This step is one of my favorites. I really enjoy SAC traversals. And as I like to think of it, the SAC step in Gremlin is kind of like giving an empty bag or a sack to every Gremlin traversal that's running around your graph. The Gremlins carry their bag as they walk around the graph, and they pick up and collect things about the graph to store in your bag. Possibly, using this sack, you could instruct your Gremlin, say, to pick up, calculate, and store something in the bag as it's walking through the graph structure. For example, kind of imagine a Gremlin that could walk around and collect the total number of vertices or edges that it walks through by maybe summing up an integer in its bag. Then, at the end of the traversal, you could inspect the contents of the sack or the bag to maybe see how far that Gremlin has walked throughout the graph. So let's visualize this. You can imagine that the Gremlins in this graph represent the full journey of one Gremlin traverser from left to right. That is, the Gremlins started on the vertex at the far left of the graph and walked the full path all the way to the right. To start, let's imagine that the Gremlin on the very far left vertex began his journey with an empty bag. Then, as the Gremlin walked to the right, he added 1 into his bag for every edge he walked over. So when you inspect the sack for the Gremlin at any vertex, it'll contain the number of edges the Gremlin walked to get there. At the end, we would inspect the value at the sack and find a value of 5, representing the 5 edges that our Gremlin walked from left to right in our graph. While as a visual, that may make sense, let's dive a little bit deeper and create a more concrete definition. In its most simplest form, a sack is just an object or a data structure that is local to the traverser. You're required to initialize the sack with a value or an object, such as 0 or maybe an empty map. As your traverser moves throughout the graph structure, you can update the object in the sack, or you can read the values of the object, maybe to make a decision about your traversal. It is important to note 2 things. First, unlike side effects, which are global data structures visible to all traversers, sacks are local data structures visible only to their respective traversers. Secondly, unless explicitly initialized, traversers do not have sacks. Unless you happen to be a handbag aficionado, why would you want to give your Gremlin a sack? Well, for starters, sacks are really useful in collecting path information or computing decaying energy algorithms throughout your graph structure. Also, in general, sack-based traversals have a smaller memory footprint than path-based traversals for 2 reasons. First, sacks usually contain values like the path distance rather than the full path history. And second, traversers with sacks can be merged, while traversers with path data structures cannot be bulked. While they are extremely useful, sack-based traversals may not outperform path-based traversals 100% of the time. A lot depends on the path characteristics, the graph's branching factor, and how much bulking is possible. We will get into the differences between bulking and merging in a later example, but for now, it is important to note that bulking is something you can do with any traverser, whereas merging is something that you do specifically during the sack step. As with any new concept, let's introduce the new steps, their parameters, and some common usage patterns. First, we have the with sack step. The with sack step enables sacks in your graph. It is the way that you can create a sack for each Gremlin traverser. There is 1 required parameter and 2 optional parameters. The first parameter, initial value supplier, is required, and it provides the initial value for each traverser's sack. Next, you can provide a split operator. The split operator is a unary operator that clones the traverser's sack when the traverser splits. If no split operator is provided, then identity is assumed. This essentially tells the traverser what to do when it moves from a vertex and goes out multiple edges. The split operator defines what to do with the sack and its values when the traverser split from 1 to many. After a split, we need to consider what to do on a merge. That's the third parameter of the with sack step. The merge operator is a binary operator that unites 2 traversers' sacks when they are merging from multiple traversers into 1. If no merged traverser is provided, the traversers with sacks cannot be merged. You can picture this when multiple Gremlins take different routes and end up on the same vertex. The merge operator indicates what the traversers are to do with the values in each traverser's sack. The next steps to introduce are those which allow us to mutate, update, or inspect a traverser's sack. The Stax step is used for these functions, reading the Stax value and writing to it. The Stax step with no parameters reads the Stax value and places it in the traversal stream. The Stax step can also take an update function, which will update the Stax based on two things. First, the existing object in the Stax, and second, parameters supplied by the step modulator. Common update functions that I use or have seen used are sum, min, and mean. That'll become more clear as we look at the examples. And before digging into the examples, let's take a look at the by modulator. We have seen the by modulator in a few different Gremlin topics in this series so far. As far as its use with the upcoming examples, we will see that the by step modulator is frequently used to pass additional parameters for computing a new Stax value. Since we have seen the by modulator a few times, let's dig into the examples to get an idea of exactly how to use this with the Stax step. As before, we will be using the killer video graph schema, where users know users, users rate movies, and movies belong to genres. We also have other people in our graph that act, direct, compose, and have created the movies in the sample dataset. Before looking at some code, let's begin understanding the Stax step with a visual example. You can imagine that this graph represents you, shown there in the middle next to the start arrow, and then your social network. And if you are not 17, maybe you can imagine somebody else in your life who is 17, just so you can walk through this example. What we want to do is use the Stax step to start from you and add up all of the ages of your friends and your friends' friends. To do that, we would drop one traverser at the starting vertex with the Stax initialized to 0. Then, the Stax will grab the age on the current vertex, which is 17, and add it into the gremlin's Stax. Next, this traverser is going to split into 4 total traversers and move to the adjacent vertices. At this point, each Stax is going to have a local copy of the integer, which is still 17. Let's follow the traverser in this graph that moved up, or to the vertex directly above the starting point. This traverser arrives at the new vertex, grabs the age of the vertex, and adds it into the Stax. At this point, the current value in the Stax is its previous value, 17, plus the new value of 17, for a total of 34. From here, the traverser splits again and continues to move up. The traverser that followed the branch up and to the left will arrive at a vertex with an age of 16. And as you see right above in the equation, the total value in this traverser Stax will be 17 plus 17 plus 16, which is 50. That means that the total age of the friends observed on this path is 50. The traverser, which moved up along the branch to the right, will reach a vertex with an age of 17. And as you see above that vertex, the total value in the traverser's Stax will be 17 plus 17 plus 17, which is 51. That means that the total age of the friends observed along this path is 51. As you look around this full graph example, you will see that there are a total of 13 different paths, and therefore 13 total traversers that would be generated throughout this process. Given this visual example, let's take a look at some code of how to do this with the Stax step. We have 2 different ways to write a Gremlin traversal that does the very walk that we just stepped through on the last slide. The first traversal here on the slide shows you how to do the aggregation as you walk through the graph. To do this, the first line of the traversal calls g with Stax 0 to create a Stax for the traversal and initialize its value to 0. On the second line, we find our favorite user, good old U1. Starting at this user, we add its age into the Stax. If you remember the visual mental walk we did on the previous slide, at this point, we have added 17 into the Stax value. We do this by calling the Stax step, passing the Stax step the sum update function, and then indicated what values to sum with the subsequent by modulator. Here we say to sum the value age into the Stax for that traverser. We want to do this process for our friends and the friends of our friends. So to do this, we will need the recursive step repeat. To do this, we will need the recursive step repeat. And you see that at the end of the repeat step, we say we only want to do this repetition 2 times, meaning that we are only going to do some work for 2 neighborhoods out from our starting location. Inside the repeat step, we tell the traverser to walk out the nose edge to the next vertex. Once at the adjacent vertex, we call the Stax step. Give it the sum update function and tell the traverser to add in the age value into the gremlin Stax. Once we have done this for our friends and the friends of our friends, we inspect the value in gremlin Stax by calling the Stax function. And now we will see the full list of all 13 values previously seen on the last slide. The second example shows us how to do this without using the Stax step. However, we will then need to use the path step so that we preserve the full history of every traverser so that we can have the ability to sum up all of the ages. To do this, we find our favorite user, good old U1. Next, we use the repeat step to walk out the nose edges 2 times. This is the same as before, and it traverses out to the second neighborhood from our starting location. Lastly, we call path and represent all of the objects in the traversal stream by their age. Then we apply a sum to each traverser locally. The use of local here makes sure that each of the 13 traversers sum up the ages in their individual path, instead of summing up all of the ages observed across the full graph. And as we hope, we see the same 13 ages as before. In this example, we want to show you how to use the value in Gremlin Stack to make a decision within the traversal. For example, maybe we want to keep walking through the graph until we collect a specific amount of data. So in this example, we're going to find a path that starts with our user U1 and eventually adds up to a total of 200 or greater. To initialize the traversers to have a SAC, again, we start with g.withSAC 0. Then we find user U1 and sum user U1's age into the SAC. Next, we see a repeat until pattern. Here, we want to continue to walk out the nose edges, and we want to continue summing up the observed ages in the SAC. We want to do this until the SAC value is greater or equal to 200. Then, we call the path step on the traversers that pass through the repeat until filter. We inspect the path objects, which are all users, by their user ID. We limit the results to only one path and we unfold it. Here, we see that the collection of U1, U74, U750, 775, 572, and U277 have a total age of 204, which is greater than 200. Next, let's dig into an example that's a little bit more complicated than keeping track of a number. Let's walk through the graph and instead keep track of an object, like a map. When we start using more complex data structures like maps or lists, it's vital to make sure we define a split operator. We need to define a split operator because the default operator is the identity operator, and that probably will not give you the behavior that you expect. In this example, we want the same behavior that we have been using in the previous examples. We want to create a copy of the SAC and its value that is to be passed on to the traversers when they split. Then, we want each traverser to have their own instance of the SAC object and its value so that the traverser can update the object during its walk throughout the graph. To do this with a complex data structure like a map, we need to define the split operator to be clone, as we see here at the beginning of this example. Using the clone split operator gives each traverser its own copy of the map. Otherwise, without defining the split operator, it would use the default behavior, which is the identity function. When using a more complex data structure like a map, this would mean that each traverser would be updating and reading from the same global object through the traverser's local reference to that object. This is probably not the behavior that you would expect. To initialize the SAC function to be a map, we call g.withSAC and instantiate the SAC to be a map with the map notation seen here. Next, we want to define the split function to be clone. This guarantees that each traverser will receive its own local copy of the object. We want this object to be a map of users and their ages. To do that, we start by traversing to our favorite user, U1. On the second line, we call the SAC function to update the map in the traverser's SAC. What we want to do is to create a key in the map that is U1, and we want that value to be U1's age, 17. We can do that by creating a custom function. This function is a lambda function that takes 2 parameters. The map and the user vertex. These parameters are shown to the left of the arrow in the lambda function notation. To the right of the arrow, we define how we want to use those parameters. We want the map to have a key, and we want that key to be the user's ID. We want the value to be the user's age. Then, we return the map into the traverser's SAC. All of that was just for putting in the very first value of the map. At this time, if we stopped the traversal and inspected the map, we would see U1 and 17. Next, we want to repeat the same process as before. We want to traverse to U1's friends and then the friends of U1's friends. Along the way, we want each traverser to collect the user ID and that user's age, and then insert that data into their SAC. We do this, just as before, with a repeat step with a limit on the number of times. We only want to do this 2 times. Then, inside of the repeat step, we walk out the nose edges to get to another user vertex. On that user vertex, we want to update the traverser's SAC. We do this update with a lambda function inside the SAC call, as we saw before. We have 2 parameters. the Stax map, and the object the traverser is currently on, which is a user vertex. We create a key in the map that is the user's ID, and the key's value is the user's age. Then we return the map to the traverser's stack. After repeating that process 2 times, we want to see the object within the stack, so we call the stack step to read the contents of the traverser's stack. We limit only one traverser and look at the results. We see a map with U1 and its age of 17, U74 with an age of 15, and U40 with an age of 12. While this was a pretty big example, the main things to remember are, first, with split, each traverser gets a copy of the starting or initialized map. Second, the updates to that map are local to the individual traverser's stack. Third, with complex objects, you probably want to define the split function to be cloned, because without split, the traversers would be updating a global object through a local reference. Now, once we have instructed our traversers on how to split, naturally, we need to tell them how to merge. In our last example, we want to dig into the merge operator and how it enables bulking optimization for better performance. Before digging into this example, it's important to clarify the difference between bulking and merging. Bulking is the word for combining traversers that reach the same object in a traversal. You can picture this as 10 gremlins running around and eventually arriving to the same vertex. With bulking enabled, the 10 gremlins are going to be combined into one larger gremlin with a bulk value of 10. Bulking is something that you can do with any traversal, not just the Stax step. Conceptually, bulking is very similar to merging. However, the word merging is reserved to an operation with the Stax step. When using gremlin Stax, merging defines how the values in the traverser's stack are to be combined or merged when 2 or more traversers are bulking together. Think of the same example where we had 10 gremlins running around the graph and they all arrived to the same place. If those gremlins all have stacks with objects or values, we need to tell them how they are to combine the data in their stacks into one. This is the process called merging. Merging is something specific to the stack operator, which tells the gremlin traversers what to do with the values in the stack when they are being bulked or combined together. To illustrate the difference between these concepts, we are going to walk the graph shown on the right part of this slide. We're going to start at U1 at the top, and then we're going to walk down each path to get to U493. The first example does not have a merge operator, so we're going to have 2 traversers with data to inspect. The second example introduces a merge operator. The 2 traversers that arrive at U493 are going to bulk together and merge their data into one stack. The output will only have one traverser. To really dig into this, let's walk through the code. In the first example, we start with g.withStack and initialize the value to 0. Then we start our traversal at user U1. We add user U1's age into the stack. As we have seen before, we repeat walking out the nose edges, and we add up the ages of the vertices into the stack along the way. We traverse 3 nose edges and reach user 493 at the bottom of the image. Here, we call the stack function, and we see that we have 2 traversers. One traverser was 65, and the second traverser was 72. We expect to see 2 traversers because we did not define a merging operation, and so we saw each traverser, even though they ended on the same result vertex. In the second example, we want to define a merge operator. We start by saying g.withBulk false, withStack 0 sum. I'm going to cover what is occurring with the initialization of withBulk false a little later. The important part to note here is the definition of the merging operator within the withStack statement. We are indicating that the merging operator here will be sum. That means when 2 traversers need to bulk or combine from 2 into 1, we will merge the stack values by adding them up. Next, we want to start our traversal at user U1 and add U1's age into the stack. Again, we repeat this 3 times, walking out the nose edges and adding the user's ages into the stack. Once we have reached user 493, we inspect the value of the object in the stack by calling the stack function. Here, because we had a merging function, we only see one value, which is 116. Now, if you look at the path values from the last example, you'll see that 65 plus 72 is 137. However, because we were using the bulking optimization, the 2 traversers arrived at 493, bulked together, and then added their stack values. This augmented the stack with the age from 493 only once. This keeps you from double counting user 493's age into the stack. Now, back to the withBulk false initialization. We used withBulk false so that we did not output the same result multiple times for the same traverser, which had a bulk value of greater than 1. In other words, withBulk only affects output formatting and not actual execution. The bulk value keeps track of the total number of traversers that are combined together into the single traverser so that we know how many had been removed through the bulking optimization. And that is it for the Stack traversal, bulking, and merging. I know that was a significant amount of information, so give the exercise a try and we will be here ready to dig into the next topic.